Hey everyone! So in this video I like to talk about rates of change and slope. So in mathematics we're often concerned with identifying or analyzing the different relationships between two varying quantities, right? Two variables. And so the ways we've done this is we've built graphs or we've worked with equations and tables. And one important relationship that we can measure that I'd like to introduce today is how much one variable changes when we change the other variable. So this idea is called a rate of change. So measuring how much one variable changes as we change the other variable, this idea is called a rate of change. And here, I'll get a little bit more specific with this in just a moment, but let's first go over a very explicit example to motivate this idea. So this next example involves pottery. And so here, let me describe a little bit about pottery. So usually with pottery, you're starting with maybe a piece of clay that's wet, and you sort of shape it or make the form of it. And what you want to do is you'll let it dry to let all of the water get out. And then later you'll put it in a kiln and really heat it up to solidify this shape. And here, this problem says that in order to fire a particular kind of pottery, the pieces must first be cured, so dried, by raising the temperature slowly and evenly. And so it says that Sonia checks the temperature in the drying oven at 10-minute intervals and records the following data. So we've got a table here where the input variable is time and the output variable is the temperature. We have all of these different points. And so it says that the heat in the oven should not increase any faster than 0.5 degrees per minute. So sometimes if the potter or the clay gets heated up too fast, it'll crack and the piece will get ruined. And so here it's just saying for the piece to be safe, we want to make sure that the heat in the oven doesn't increase too fast, doesn't increase faster than 0.5 degrees per minute. And so we're tasked with figuring out, is the temperature in this oven within the safe limits? And so here we have to make sense of the data in this table. We need to decide whether or not it satisfies this condition here, that the heat in the oven does not increase faster than 0.5 degrees per minute. And so the first thing I want you to notice is that this 0.5 degrees per minute, this is a rate. Right, so this is a ratio of 0.5 degrees for every 1 minute. Right, this is really describing a change in temperature. Right, we don't want the oven to increase its temperature, to change its temperature too fast, faster than 0.5 degrees for every change in time of 1 minute. And so what we can do when we look at our table here to confirm or verify whether or not this oven meets the safety conditions is we can look at the different temperatures at different times. And so here, if I look at this temperature of 70 degrees at 0 minutes, I want to figure out how much the temperature increases for every minute. And so I need to actually look at two different data points, right? I need to look at another point where I can see how much the temperature increased. How fast is this temperature increasing? Well, here, in this case, it increased 4 degrees across those 10 minutes. And so here it's important to kind of keep in mind both the temperature increase and the time increase, right? Those two together play an important role in this story. Right? So it's not just important that there was a 4-degree increase. This 4-degree increase, most importantly, happened over the 10 minutes. And so if we look back at the change in temperature and we compare it to its change in time, well, what we get here is, let's see, where should I write it? So here, what we get here is, well, we get a 4-degree increase. So maybe I'll do this with colors. So 4 degrees. There's an increase in the temperature by 4 degrees within this 10-minute interval. And so we're not really interested in what the rate is for every 10 minutes. We're interested in how much it is per single minute, right? Well, we can rewrite this 4 degrees over 10 minutes as 4 over 10 degrees per minute. Right, as this unit interval. And 4 over 10, well, this is the same as 0.4, right? You know, this over 10, this is kind of like splitting up our whole part into 10 different pieces, and we have 4 different pieces, 4 of those different pieces, right? So if I have $1 and I split it up 10 ways, I have 10 cents. And if I have 4 sets of those 10 cents, I have 40 cents, right? 40 cents out of $1. So this 4 out of 10 is 0.4, and this is the degrees per minute. And so this is telling us that actually this oven here, at least during that first 10 minutes, is meeting the safety limits or safety conditions, because 0.4 degrees per minute is less than 0.5 degrees per minute, right? The oven should not increase any more than 0.5 degrees per minute, and it does satisfy that. And actually, we can look at all of the other 10-minute intervals, right? If I look at all the other 10-minute intervals, we see, well, actually, there's also only a 4-degree increase every single time. Okay, so this oven is increasing its temperature at a very consistent and even rate for every single set of 10 minutes. And so we saw that in the first 10 minutes, that amounted to a 0.4 degree increase, and so that was safe. And so actually all the temperature, or every 10-minute interval, it seems that the temperature increases is at a safe amount. So in this last example, we measured the ratio of the change in the output variable to the change in the input variable. Right? We measure the change in the temperature, and we divide this by the change in the time, the change in the number of minutes. And so this amount was telling us how fast the temperature was increasing in that oven every minute. And so we call this kind of ratio, the ratio of the output variable to the change in the input variable, we call this a rate of change. Right? It's telling us how the output quantity is changing in comparison to the input quantity, changing the input quantity. And so this idea appears so frequently that we give it some special, there's some special notation we use to sort of make things a little bit more concise. Right? So here in the last example, we saw that we called y, this y variable, we called it the temperature. We let that represent the temperature, and x in that last example, we let that represent the time in minutes. And so we saw that we were interested in the change in the temperature, and we divide it by the change in time to get that rate of change, to get that rate of change of the temperature for every minute, how fast the oven was heating up. And so here we might write this as, we'll use a special symbol, it's kind of this triangle here, it's the Greek letter delta. And we use that to represent the idea of change. So here, we might say that the change in temperature divided by the change in time, we might write that as delta y divided by delta x. So here, this symbol delta, this is the Greek letter delta. And it's usually used to denote change. So this is another way we might concisely write change in y divided by change in x. And so here, if we want to find, and this is what we typically think of when we talk about rate of change, is the change in the output divided by the change in the input, delta y divided by delta x. And so here, maybe let me ask a related question. So what is the rate of change? Maybe I'll say between here are the two data points we had earlier, 20, 78, and 50, 90. So here, these are 2 points that we saw in our table a moment ago, and specifically these points, right, 20, 78, this was saying at that 20-minute mark, the temperature in that oven was 78 degrees. And here, this point is saying that at that 50-minute mark, the temperature in the oven was 90 degrees. And so if we want to figure out the rate of change between these two different points of time in the oven, well, we just need to figure out the change in the temperature, the delta y, divided by the change in the time delta x. And so here, if we have those 2 points, well, the change in y divided by the change in x, the change in y is how much change there was to get from 78 degrees to 90 degrees. Well, that's an increase of 12 degrees. And here, I like to write down the units because they really describe the situation quite well. And I really think once we get to our answer, it's an answer that makes more sense when the units are involved. So 12 degrees. And then what's the change in x, delta x? Well, that's how much time passed right here to get from 20 minutes to 30 minutes. Or 20 minutes to 50 minutes. That's a change of 30 minutes. So this is the rate of change between these 2 points in time for our oven. And if we simplify this a little bit, this is 12 over 30 degrees per minute. And we can rewrite this as, well, I can see that this simplifies the numerator and the denominator. They're both divisible by what's the largest number that divides 12 and 30? I think 6 divides 12 and 30. I can write this as 2 over 5. And actually, that's the same as 0.4. Actually, maybe it would have been simpler to just divide this out both by 3, and we can see that we get the same fraction we got earlier, right? If I divide the numerator and denominator by 3, I get an equivalent but more reduced fraction. Dividing the top by 3 gives us 4. Dividing the bottom by 3 gives us 10. This is 4 over 10 degrees per minute, which we saw earlier was also 0.4 degrees per minute. So we ended up getting the same, and that's because earlier in our example, the oven was increasing its temperature at a very even, consistent rate. And so we got the same rate of change later on between these 2 points in time as we did earlier. So in this next example, we're given a table that shows the price labeled with the variable P for G gallons of gasoline. And so we're asked to plot the points on a coordinate plane. So I've got a coordinate plane shown below. And then the next thing we're asked to do is, what is the rate of change, to find the rate of change between between 2 data points. Doesn't matter which 2. And so here, let's plot these points onto a coordinate plane. So we've got the point 4, 6, and so our left column, that's our input variable. It's the number of gallons. So I'm going to label that horizontal axis with the variable G. Our output variable, that right column, that's our variable P for the total price. So that's our vertical axis. And so we've got the point 4, 6, right? So 4, 6. Here, if I look at this grid. Here I can see that every little horizontal tick mark, that's another single unit. So here, this is 4 on the horizontal axis, but that's not the point, right? The point 4 comma 6 is here, right? Oops, sorry. Sometimes when I try to really fill in a dot for too long, my tablet thinks it means something else. So here, there's the point 4 comma 6. Because when we look towards our p-axis, we have a p-value of 6. When we look to our g-axis, we have a g-value of 4. Okay, so we've got 4 comma 6, 6 comma 9. So that looks like that's about here. We've got 9 and 13 and a half, 9 comma 13 and a half. So that's, here's 11, 12, 13, 13 and a half. And then we've also got 12 and 18 and a half, 12, 18 and a half, it's about there. And then 15 and 22 and a half. So here's 2250, right? 15 comma 2250. And we can see that these points all lie on a line. So maybe let me draw out that line. Just a rough sketch of this line. Okay, so that's a very rough sketch, but I think it gives us an idea, and maybe let me just emphasize the points that we plotted out a moment ago. So these are the points from the table. Okay, so here we've done the first task. We've plotted out the points on the coordinate plane. They fell on a line, and we sketched out that line. So the next thing is, what is the rate of change between two data points? And so here, it doesn't matter which 2 points we use. Let's use the first 2. Right, so here, we're asked to find the rate of change, and so this is saying what's delta, in this case the output variable is p, delta p divided by delta g. Right, so this is representing the change in price between our 2 data points divided by the change in gallons. Okay, and so if we use our first 2 points, well, what's the change in price? Well, to go from the first price to the second price of $6 to $9, well, that's a change in $3, right? That's a $3 increase. And that's a $3 increase for, what are they getting that from that additional $3? That's for 2 more gallons, so plus 2 gallons. And so what we're saying is that the rate of change between these 2 points here, the change in price is $3. So maybe I'll just write out dollars instead of using the symbol. So $3 over 2 gallons. And so we can rewrite this as, this is 3 over 2 dollars per gallon. And 3 over 2, that's the same as 1.5, right? 1.50. So this can be seen as $1.50 per gallon. So this is telling us a rate of change, right? What we did find was a rate of change, a change in the output divided by the change in the input. And this is really telling us how fast the cost is increasing for every additional gallon. And here it's telling us that it's a $1.50 increase in the output for every single one increase in the input, one increase in the gallons. So we've taken the time to plot out the data from this table. Here, maybe let's take a moment to interpret what does rate of change look like on a graph. And so here, we've figured out the rate of change. We figured out the change in the output, and we figured out the change in the input between the first 2 points from our table. So what does that look like in our graph? Well, change in P. Right, change in P, delta P, or this is the change in output, in this case the price, graphically, this is the vertical distance between 2 points, right? This is the vertical distance between 2 points. And typically, if we're dealing with just the x and y variable, we would think of the change in the output as delta y. And delta y, that would just be the vertical distance between 2 points. That's really what the numerator and the rate of change is describing, the vertical distance between 2 points. And then similarly, if we have, in this case, it was delta g, right? The g is the input variable. This was the change in the input, in this case, the gallons. And really, this is just describing the horizontal distance between 2 points. And so if we look at this picture here, we were really dealing with the first 2 points from our table. And if we look at what the vertical changes between these 2 points, if we really are looking at this delta P that we saw of $3, well, that was the change in the y values. It's really these 3 units there between the 2 points, right? The difference in their heights, their output values, their P values. Okay, so this was delta P, right? The change in that numerator, or the numerator and the rate of change. This was the change in the price. This is delta P. This was $3. And then what was delta G? That's the change in the input between these 2 points. And maybe I'll be a little bit more precise with that. That was these 2 units here. This is delta G, and this is 2 gallons. And so really, the rate of change is this ratio of the vertical distance between 2 points divided by the horizontal distance between those same 2 points. And so maybe I'll write that down, and that's a very important idea. So the rate of change is the ratio of, right, it's a change in the output, and really that's the vertical distance between 2 points divided by the change in the input, which is the same as the horizontal distance between 2 points. And so here, in this picture, we can see that vertical distance is 3, that horizontal distance between those 2 points is 2, and so we get that rate of change of 3/2 dollars per gallon, like we saw from our computation from our data points. So some other language that we'll use to refer to the same idea as this rate of change is this word slope. So this is also called the slope. So when we have a rate of change, we compute or determine some sort of change in the output divided by the change in the input. We said graphically, that's really the same as finding the, if we have 2 points, the change in the vertical, or the change in the y values, the output values, it's the vertical distance between those 2 points. And the change in the input values, that's the horizontal distance between those 2 points. And if we're really dealing with like a line, usually if we're not really thinking of a situation, we're just looking at an equation or something. When we talk about the change in the outputs and divided by the change in the inputs, we refer to that sometimes as the slope. And so here, let me write down all those ideas together. So here, oftentimes, when we're computing rates of change, so the rate of change, the change in the output divided by the change in the input, this might also be referred to as the slope, usually when we're dealing with lines. And we said this is the change in the y-coordinate, the output coordinate, divided by the change and the input coordinate between 2 points, and we might more concisely refer to this as delta y divided by delta x. So for this next example, we're asked to find the slope of this line below using the points A and B. Right, so here, what we establish is that slope, this is the same idea as the rate of change, and really this is just asking us to find the change in y between these 2 points, A and B, and divide that by the change in x. And so here, if I look at this point A and this point B, well, what's the change in y? The change in y is this distance here, right? But specifically, if I'm going from point A to B, I'm starting at a y value of -2, and I'm going down to a y value of -4. Really, this change in y is -2, right? The y value decreased. And if I'm continuing this way, if I'm going from A to B, well, what's the change in x, the horizontal distance between these 2 points? Well, that's +4, right? I'm going from an x value of -2 to an x value of +2. That's a change of +4 in the x values. And so this can be seen as -2/4. That's our change in y divided by change in x. And this is a ratio that we can simplify as -1/2. And so all this to say that our slope is -1/2. And so here this slope is telling us how much our y value is changing when we change the x values. Right, so maybe more specifically what it's really telling us is that if we move 2 units right, this corresponds to, maybe I won't use an arrow there, I think it's a little confusing. Moving 2 units right corresponds to moving 1 unit down. To find another point on our line. Right, so here, what our slope or our rate of change for this line is telling us is that if we go 2 units down and 4 units to the right, we'll stay on this line. That's what this slope is telling us. And really that ratio of going down 2 units and 4 units to the right, that's the same as the ratio -1/2. So right, what this is really telling us that if I go down 1 unit and I go to the right 2, I'll find another point on this line. That's what this slope is telling us in this example here. And so here, we saw earlier that if we have this slope of -2/4, well, that's really just telling us that if I go down 2 units, I need to go 4 units to the right to stay on my line. So that's really what our slope is describing for this line. How much we need to, how much change in y we have for every change in x. And maybe another way you can see this is this is telling us we have a slope of -1/2. Well, this is saying that if we move, similarly, if we move -1/2 units down, that corresponds to 1 unit right. Right, so here if I go down by 1/2 unit, right, it's my change in y per change in x is -1/2. That's telling me if I go down 1/2 unit, I need to go right 1 unit to stay on my line. If I go down 1/2 unit, and if I go right 1 unit, that'll correspond to me staying on my line. So here this last example says that the graph below shows the distance traveled by a driver for a cross-country trucking firm in terms of the number of hours she has been on the road. So here it tells us the distance traveled by a particular driver based on the number of hours they've been on the road. That's what this graph is here. And so here we want to determine the slope of this line. And so what that means is we need to take 2 points on this line and find the change in the outputs divided by the change in the input. So here I'm going to take these 2 points here. I'm going to take this one, and maybe I'll take this one out here. And so if I want to find the slope, I need to find the change in the outputs. So that's this distance here between these 2 points. If I'm kind of imagining starting at this bottom point and going to this top, well here, I would need to have an increase in my y values of, I'm going from 100 to 250, right? So that's a change in y. This is delta y here is 150. And then what's delta x? What's the change in x? Well, here, that's just 3. And so what are the units here? Let's include those to really make this very explicit. So here, the outputs were telling us how much distance was traveled. So maybe I'll label this axis D for the number of hours. So here, I'll label this T to describe time in hours. So this is 150 miles, an increase of 150 miles over 3 hours. So change in y, delta y, divided by delta x. This is equal to 150 miles over the course of 3 hours. And so this is equal to, 50, right, 150 divided by 3. This is miles for every 1 hour, 50 miles for every 1 hour, or 50 miles per hour. And so what is the meaning of the slope? Well, the meaning of the slope is really just taking the units of the output variable and dividing it by the units of the input variable. Here this is telling us 150 miles divided by 3 hours, 50 miles per hour. It's giving us a speed or a velocity, right? So the slope was 50 miles per hour. And this is giving us the rate of change of the distance in terms of the time. This is giving us an average speed or velocity.